Hello everyone, I'm Alessandro Perelli, lecturer in biomedical engineering at the University of Dundee, and I'm going to present our work on multimodal 3D brain tumor segmentation using generative adversarial network and conditional random field. This work has been developed with the student Lan, Yu Chao, Miao, Ai Qing, and Fatima. In this work, we concentrate on MRI imaging, which is a widespread technique that produces high-quality images, and we're particularly interested in human brain. The crucial point is that it's possible to exploit different MRI sequences to generate multimodal MRI images which have different contrast. This can be used to improve the analysis of anatomical or pathological features. For example, in yellow, the FLAIR image can be used to identify clearly the boundary between the whole tumor and the healthy tissue, while the T2 modality can focus and highlight the edema area, so the tumor core, and then the T1 image can be used for analyzing the enhanced tumor. So these multimodal images can be used essentially to perform a semantic segmentation, which means that we can generate a label, a color label, with each class separately for the whole tumor, tumor core, and enhancing tumor. This work will focus on the 3D brain tumor segmentation for these 3 tumor subregions using advanced deep learning network. State-of-the-art approaches for semantic segmentation includes the encoder and decoder architecture, such as the UNet or the convolutional neural network. These are very popular architecture, as well as generative adversarial networks, which are based on blocks, generator and discriminator that are, and the discriminator needs to be able to identify whether the generated image are real or fake. Now, our work is based on the GAN backbone, and we introduce different novelties in order to improve the accuracy of the multi-class semantic segmentation and also the computation. So the aim is essentially to develop from the GAN network, where we have the 3D multimodal array of MRI images, T1, T1C, T2, and FLAIR. This is the input for the generator and also is used as a guidance for the discriminator. The generator needs to generate the multi-class segmented image, and the result is enhanced in terms of smoothness using a conditional random field layer. The output of the generator is then sent to the discriminator, which is used with the guidance of the image and the ground truth, and the discriminator needs to decide on whether the image is fake or real. The output will then be used to update the parameter of the generator and discriminator in a min-max fashion. Our model, we call it 3D VGAN, and the key components are using 3D input, which allows to improve the accuracy by exploiting the correlation between contiguous slices, using pseudo 3D convolutional layer instead of full 3D convolutional layer. This allows to reduce the computational need during training, and then the use of conditional random field to enhance the details in the label. The conditional random field module is constituted by a Gaussian bivariate potential function, the mean value approximate inference. So in terms of the actual implementation of these mathematical blocks, this has been designed using a recurrent neural network layer attached after the generator. This has the objective to enhance the spatial continuity and then to accurately locate the predicted pixel locally. Overall, this helped to have a smooth and accurate image segmentation. In terms of the training of the 3D vegan network, the loss function is constituted by the generator loss and discriminator loss. Regarding the generator loss, this is constituted by two terms: the L2 bias between the original image and the label, plus the generalized dice loss, GDL, between the ground truth and the predicted segmented image. There is a factor alpha which balances out these two terms. The discriminator loss is constituted by the L2 bias for the original image, so there is the guidance and the label, and then the bias between the true label and the predicted one. So the key component here is the fact that to improve the min-max training, we guide the discriminator loss using the information coming from the original image, and this is the same, is also encapsulated in the generator loss. In terms of the actual architecture of the generator, we use a modified VNet where the input are the 4 3D array channels for the 4 multimodal MRI images. The encoder has a backbone structure of the ResNet, and we deploy different configurations with different layers, and the type of filter and configuration is defined in the table below. Then the decoder part, which is considered essentially by convolutional layer and upsampling, and then the output, which is the 3D segmented label of the full volume. To validate the results, we have used the BRATIAS dataset 2018, which is constituted by 3D brain MRI images for 4 modalities: T1, T1C, T2, and FLAIR. And then we deploy the training using a dataset of 285 cases, where we highlighted the region of interest of 240 times 240 times 155 for the high-grade glioma and low-grade glioma MRI images, and we use 66 cases for the validation set. In terms of training results, for the loss, here it's shown on top the L2 loss and bottom the DICE score, for in red the training and in blue the validation. So it's possible to see how the convergence is quite fast in terms of epoch number, and also the discrepancy between validation and training is small, especially for the L2 loss. In terms of the qualitative results, so we obtain good agreement between the qualitative ground truth slices, MRI images, and the predicted one for all the different modalities, and also in terms of segmentation in the bottom, we can see the input slice for the different multimodal MRI, and then the 3D vegan segmented output. In terms of quantitative results, so we first perform an analysis on the weighting parameter of the generator loss, alpha, and then the results shown that an alpha value of equal to 5 leads to the best performance in terms of the different quantitative metrics, DICE score coefficient, sensitivity, specificity, and Hausdorff distance. In terms of the contrast segmented quantitative results, we perform a comparison with different standard networks such as UNet, GAN, a fully convolutional network, 3D VNet as well. So this is a combination of 2D and 3D network and ours. And we were able to show noticeable improvement consistent through all the metrics evaluated. Conclusion, we have proposed enhanced GAN architecture with the key component of taking into account the 3D full multimodal MRI images with input guidance of the discriminator and with the employment of a conditional random field module to improve the label generated by the generator. In the future, we envision the fact that this architecture can be extended into a two-stage cascaded framework, where the first stage, simple one to highlight the whole region of the tumor, and then the second stage can be improved as a refinement to identify the smaller tumor core and enhanced core region. Thank you for listening, and we hope you enjoyed this work.